Hello there, little boy. Trying to pick out a drink, I see. Why not go for the milk? It's nutritious and contains a healthy dose of calcium. While we're on the topic, let me tell you about the element of calcium. Alright, son, here we have a periodic table of the elements and an atom model of calcium, which you can find in that milk right there.
Okay.
As you can see, there are 40 dots in the middle or nucleus of this atom model. This isotope of calcium, or the different form of this element's atom, has a total of 40 protons and neutrons, which is where the number 40 comes from. This aspect of the calcium atom is represented on the periodic table, along with calcium's other isotopes, as the atomic weight. On the table itself, this number represents the average between the isotopes of all the atomic weights of all the isotopes of calcium. But this isotope's atomic weight is exactly 40 for its proton and neutron count.
Alright, but why are some dots in this isotopy, whatty, or whatever differently colored than the other dots? It looks like half are one color and half are another color. Does that represent something?
It sure does. One color, as you see here, represents the number of protons, and the other represents neutrons. Protons are positively charged particles in the nucleus, and neutrons are negatively charged particles in the nucleus.
So you said that there are these proton and neutron thingies in the nucleus, right? Well, anyways, as you said, that isotope? Right, of course. That the isotope is 40, which means there is a total of 40 protons and neutrons. So how many protons and neutrons are there, exactly, of each?
Well, all elements have a set amount of protons for any given atom, which determines its atomic number. Calcium's atomic number is 20, because it has 20 protons. Isotopes are determined by the particle that can vary from isotope to isotope, which is the neutrons. Because this calcium isotope is calcium 40, and the atomic number for calcium is 20, the neutron count for this calcium isotope is 20.
Wow, that's amazing! But even though I can tell there are rows with numbers that are going up, why aren't all the elements stacked or lined up in one direction only? Why do they need to be particularly organized?
Well, first of all, the numbers you see that are going up, as I already mentioned, are the atomic numbers, or the fixed proton levels.
Yeah, I know, but why are they so particularly organized?
Well, the elements are organized into families and rows, and another classification known as state, and another known as, is it a metal, non-metal, or semi-metal? Have you ever heard of any of that?
Well, of course not. Just tell me already.
Alright, son. But first let me start by saying this.
Oh, here we go.
Don't worry, the boring stuff will soon be over. Then we'll get to the really fun stuff, like uses in construction and in nature.
Well, I'm going to drift off, so carry on already, mate.
Alrighty, son. The main families of the periodic table are the alkali metals, the alkaline earth metals, the transition metals, the boron family, the carbon family, the nitrogen family, the oxygen family, the halogens, and the noble, also known as inert, gases. Calcium is in the alkaline earth metals family. This family, as you can see on the periodic table, is in the second column, or group number 2. Each family includes elements with a set valence electron count. This applies to all families except for the exceptions in the transition metals and inert gases. All elements have electrons, which are the particles you see on the outer rings, better known as shells, of the atom model you see here. Valence electrons are the electrons on the outermost shell, and, as I mentioned earlier, Each family has a set valence electron count. Calcium's family, as I also mentioned earlier, is the alkaline earth metals, which all have 2 valence electrons. The reason elements have families that regard valence electron counts is because the valence electrons have a very high significance. Valence electrons determine an element's level of reactivity with other elements and other substances. The closer an element is to emptying or fulfilling its valence shell, the more reactive it is. The only virtually non-reactive family is the inert gases, because they already have a full valence shell. The 2 most reactive families are the alkali metals, because they only need to lose 1 electron to have an empty shell, and the halogens, because they only need to gain 1 electron to have a full shell. A full valence shell has 8 electrons. Because calcium and the rest of the alkaline earth metals have 2 valence electrons, they have a moderate to high reactivity.
Wow, that's a lot of stuff to remember, mate. But what about the rows you mentioned?
The rows are the repeating patterns on the table. Each row has the same pattern as it goes across, except obviously for those bloody transition metals, which you unfortunately need to skip in order to remember this process. Going across, the elements have 1 valence electron, then the next has 2, then you have to skip a few, those bloody transition ones again, then 3 and 4 and 5, all until 8, where you go to the beginning of the next row down and start again. Oh, wait, another thing regarding rows.
What is it?
Each row contains elements with the same amount of electron cells, or as I called them earlier, the rings around the nucleus, which you can see here in the model. It has 4 shells, as calcium is in row 4 of the periodic table.
I guess that makes sense. But what about the other classifications you mentioned earlier? Like state at room temperature or the metal, non-metal, semi-metal thing?
Yes. Those. The states at room temperature can either be liquid, solid, or gas. Calcium is a solid. And regarding the metal, non-metal, semi-metal thing, calcium is a metal, as it has the right properties to be a metal, such as good electricity conductivity, shiny appearance, and strong strength. Because calcium is located in the alkaline earth metals family, it is a metal, as well as other elements in its family.
Alright, mate. Good enough for me for one day. You do this to everyone.
Well, no. But wait! There's more! I gotta tell you about calcium's uses and such.
Well, I guess staying up past me bedtime and getting me mom all riled up wouldn't be all that bad. So, sure, mate. Carry on then.
Okay, here we go. Calcium is a very strong substance and is commonly found in construction products such as drywall when combined with sulfur and water to make dehydrous calcium sulfate, a key ingredient in drywall. In addition, calcium is found in other building product materials such as lime, which is used in cement. Calcium carbonate, a mixture of calcium and carbon, is used in toothpaste and mineral supplements. Calcium phosphate, a bond of calcium and phosphoric acids, is used to make animal feed and fertilizers. In the human body, and in the bodies of other animals, calcium is key to well-functioning bones, teeth, nails, claws, etc. While calcium is super important to your bones and teeth, it's just as important in smaller amounts to your nerves and muscles. Calcium ions are used to trigger nervous and muscle activity. In the Earth's crust, calcium makes up 4.2% of the total, making it the 5th most abundant element in the Earth's crust. But because it so easily forms compounds with oxygen and water molecules, it is not found in its purest metal form in nature. In conclusion, because calcium bonds so easily, it is very useful in building materials. Calcium's strength makes it good for fertilizer and for breaking down other materials. Calcium is extremely good for bones because it is a material that's chemical properties let it help the body.
Wow, that's finally something I can make sense of, mate. Sounds really awesome to me. And of course, I want those strong, healthy bones, so I'll be going for the milk from now on, mate. Thanks so much for helping me, Mr. Clerk.
Of course, son. And maybe tomorrow you can come into my office and we'll review some other elements too. But first, I'll show you how calcium forms an ionic bond with oxygen. In an ionic bond, a metal will bond with a gas or liquid. In this particular bond, calcium is bonding with the gas called oxygen. Calcium has 2 valence electrons, making its outer shell close to being 0, or empty. Oxygen has 6 valence electrons, making its outer shell close to being full. A full shell has 8 valence electrons. As you can see here, calcium transfers its 2 valence electrons to oxygen. This means that calcium now has a charge of positive 2. Oxygen now has 8 valence electrons, making its charge negative 2. Since same opposite charges attract, calcium and oxygen have now successfully bonded. Calcium's shell is now empty, and oxygen's shell is now full. The shells are now stable. This compound is now called calcium oxide. Oh, I almost forgot. Calcium also forms a bond called a metallic bond. This type of bond occurs between the individual atoms that make up the calcium metal. In a metallic bond, the valence electrons of each atom move freely about the crystal. This is called the sea of electrons. These electrons circulate around each atom, but move in a somewhat random pattern, as you can see here. The reason that the electrons move about freely is because they repel each other, causing them to change their positions. This flow of electrons is why metals are such good conductors of electricity. Because the electrons circulate, the ions become positively charged, as all of the circulating electrons are negatively charged. The electrons are able to move by breaking free from their original positions on their corresponding atoms. Because the electrons move, the metal itself becomes a flexible, highly conductive, malleable substance. As well as electricity, the metal is also a good conductor of heat energy. Well, now you know all about calcium. Come back tomorrow and I'll teach you about boron. By the way, I actually don't work here, so...